These are the notes for Objective 3, Right Triangle Trigonometry. In the last lesson, we became familiar with the 6 trigonometric functions, or the 3 trigonometric functions and their reciprocals, and identifying those ratios given a triangle, an angle, or an angle specifically on the unit circle. What we want to do now with this objective is take these functions and apply them specifically to right triangles and use them to find any missing information in a right triangle. As a review, the 3 trigonometric functions we're looking at are sine, which we refer to as the opposite side over the hypotenuse, cosine, which is the ratio of the adjacent side to the hypotenuse, and tangent, which is the opposite side over the adjacent side, or also known as sine over cosine. Now, if we take this information to an example triangle, we can use this to find any missing piece of information in a triangle. So let's say this angle here in the corner is 40 degrees, and the hypotenuse is 10, and we'd like to know the adjacent side. If we label our triangle hypotenuse and adjacent, we can quickly decide which of the trigonometric functions that we need to use to solve this problem. Since we want to know the adjacent side and we already know the hypotenuse, we're going to choose to use cosine to solve this problem. Setting up the ratio as if it were a formula, we can write cosine of 40 degrees equals x over 10. To solve this equation for x, we would multiply both sides by 10, and we would find that x equals 10 cosine of 40 degrees. This is a value that we can type into our calculator to get our final answer. Go ahead and try that now. Our result is that x is approximately 7.7. Generally, when we're given a number that's a whole number and trying to find a similar side, we want to round to one additional decimal place. Let's try another example. In this next example, let's suppose that instead of 40 degrees, we know the side angle is 50 degrees. We'd like to know the opposite side, and we know the adjacent side. Which of the trig functions should we use? If you were thinking tangent, you were correct. We can set up our equation as the tangent of 50 degrees is equal to x over 6. Multiply both sides by 6, and we find that x equals 6 tan of 50. Now, if we were leaving our answers exact, this is all that we would do. If we were rounding our answers or getting an approximate answer, we would go ahead and type this into our calculator and find that x is about 7.2. Let's try another example. For this next example, we're going to start knowing a side. This time, let's say the side is 75 degrees. 8. Let's say the opposite side is 8, and we'd like to know the length of the hypotenuse. Which of the 3 trig functions should we use? If you thought sine, you are correct. Setting up our equation, we have sine of 75 degrees is equal to 8 over x. Now, this is the first of our examples that we've seen where the variables appeared in the denominator. If you're familiar with algebra, you would know there's a couple of different strategies you can use, any of which apply to get the x out of the denominator. I prefer to use cross multiplication. So I'm going to put the sine 75 over 1, and I'm going to cross multiply x to sine 75 and I'm going to multiply 1 to 8. Now, divide both sides by sine 75. Remember that this in and of itself is a number. The 75 and the sine are inseparable because they represent a specific value. For our answer, we get x is about 8.3. Is that what you got? You can always double check your answer for logic, knowing that the hypotenuse is the largest side and that 75 degrees is fairly close to 90 degrees. So with 75 degrees being 8, we would need x to be larger than 8, since 90 degrees is larger than 75. Is 8.3 larger than 8? Yes. Our answer passes a logic check. Let's see one more example that you can try on your own. Solve this triangle for the missing side x. Your final answer should be 12.6. Is this what you got? The trig functions go both ways. We've seen how to use the trig ratios to find a missing side if we know an angle. We can also use the ratios to find an angle, supposing that we know both sides. This is easiest to see first on the unit circle. So as a recap, let's remind ourselves of what the values in quadrant 1 of the unit circle are. You have 30 degrees, 45 degrees, and 60 degrees, as well as 90 degrees and 0 degrees. And each of these values have a cosine and a sine. We reviewed the unit circle and where these values come from in a previous lesson. So for now, I'm just referencing them as material that you've seen before. Let's suppose that instead of knowing we had 30 degrees or 45 degrees or 60 degrees, we instead had a statement like cosine of theta equals rad 2 over 2. We know the ratio, but we don't know the angle. This is a case where an inverse function can be used. Theta would be equal to the inverse cosine of rad 2 over 2. Now we don't have to do any calculations because this value is on our unit circle. We would find cosine rad 2 over 2 and know that the angle related is 45 degrees. Therefore, the final statement is that theta equals 45 degrees. I can ask this kind of question for any value on the unit circle and for any of the trig ratios, including the reciprocal functions. For example, find theta if sine theta is 0. Well, that would require 2 of the cosine sine pairs that I did not write. In which of these angles is the sine theta equal to 0? If you answered at 0 degrees, you would be correct. Theta is equal to 0 degrees because at 0 degrees, sine is equal to 0. Let's try another one. Find theta if tangent theta is equal to rad 3. This one takes a little bit more thinking. We know tangent is the sine divided by cosine, or y over x. If you think of rad 3 as rad 3 over 1, you're looking for the angle where the y is rad 3 and the x is 1. Which of our angles does this happen for? The correct answer, 60 degrees. In 60 degrees, if you take rad 3 over 2 divided by 1 over 2, you would get rad 3 over 1 or rad 3. Now, what if the angle isn't on the unit circle? In that case, you would need your calculator to approximate the angle's value. If you look on your calculator, you should see inverse sine, inverse cosine, and inverse tangent. These three functions tend to be above sine, cosine, and tangent, and you would use your second function on the calculator to access them. So let's say we wanted to know theta. If sine theta was equal to 0.75. To answer this question, we would type into our calculator the inverse sine of 0.75. The mode settings are just as important when using inverse functions as they are when using regular functions. If you want your answer in degrees, make sure that your mode setting is degrees. If you want your answer in radians, make sure that your mode setting is in radians. Let's say for this example, we wanted our answer in degrees. What would you get? I got theta equals approximately 49 degrees. In the case of degrees, I prefer to round to the nearest whole number, unlike when I was finding side lengths, where I prefer to round to the nearest tenth. It'll depend on your question what type of rounding you should use. Let's take this knowledge and apply it back to solving right triangles. In all of the examples we've done so far, we've known the angle, but we haven't known the sides. So let's switch that. Let's say we have a right triangle, and this time we know that the opposite side is 4, and the adjacent side is 5, but we don't know the angle. We ask ourselves the same question we ask when we know the angle. If we have the opposite side and the adjacent side, which of the trig ratios do we know? If you answered tangent, you're correct. Tangent alpha equals the opposite side over the adjacent side. And since we don't know the angle, we need to use an inverse function. So we'll rewrite this equation to say alpha is equal to inverse tangent of 4/5. Typing this in our calculator, we can get an approximate value for alpha. I got alpha is approximately 39 degrees. Again, I'm rounding to the nearest whole number, which is my preference when finding missing angles, unless a question specifies otherwise. With these pieces of information, we actually know everything we need to know in order to solve a right triangle. So let's solve our first right triangle. Given the triangle A, B, C, find all missing sides and angles. So in general, when you're looking at a triangle, side lengths will be labeled with lowercase letters and angles will be labeled with uppercase letters. I would like you to find all of the values for A, B, and C if capital A is 20 degrees, lowercase a is 10. The first thing I like to do when I solve a right triangle is label the information that I have. I know that this angle is 20 degrees and that this side is 10. Believe it or not, this is all the information I need to find every missing side and angle in this picture. The first thing I'm going to look at are the angles. I know one angle is 90 degrees, one angle is 20 degrees, and the missing angle must make all of the angles add up to 180 degrees, which is the triangle angle sum. So I can find angle B by writing angle B plus 20 plus 90 must equal 180. Angle B plus 110 must equal 180. Therefore, angle B is 70 degrees. That type of scratch work isn't necessarily needed to be shown to prove. If you're familiar with the angle sum, you might have known just by looking that these two angles together are complementary and therefore must add up to 90 so that the entire triangle adds up to 90 degrees. In which case, you may have more simply just decided to say that B is equal to 90 degrees minus 20 degrees and reach the same conclusion that B is equal to 70 degrees. Either way you come to your conclusion is fine as long as you're using trigonometric relationships, triangular relationships, geometric relationships to justify your results. That leaves us with two pieces of missing information. I need to know side B and I need to know side C. Now in this case, I was able to get an exact answer for angle B. Therefore, I could use either angle B or angle A to find the missing sides. However, when we're solving right triangles, it's best to refer to the given pieces of information rather than pieces of information you solve for, especially in the case of rounding. We don't want to use rounded numbers to find more information because rounding will cause errors down the line. So with that being said, how can I use angle A and side A to find B and C? The answer, trigonometric ratios. If this is angle A, side A would be referred to as the opposite side. There are two trigonometric ratios that rely on the opposite side. The first one is sine. Sine is opposite over hypotenuse. Which of the two missing sides is our hypotenuse? The correct answer is C. The other ratio that relies on the opposite side is tangent. Tangent of 20 degrees is equal to 10 over the adjacent side, which by process of elimination must be side B. Both of these equations can be solved in a similar fashion using cross multiplication, reciprocals, or any algebraic tricks you're familiar with. Either way, we end up with the equation that C is equal to 10 divided by sine 20, 29.2, and we get that B is equal to 10 over tan 20, or that B is equal to approximately 27.5. Label your triangle with the new information that you found. And we have solved our triangle for all of the missing information. Now, it may seem redundant, but there's one value I've not explicitly written down as part of my answer, and I should. And that value is C. C is 90 degrees. Although it wasn't explicitly stated, C is 90 degrees is a part of our answer. And the fact that this was a right triangle is what allowed us to use right triangle trigonometry to solve it. Let's try that again. This time with some different information given to us. What if, instead of knowing the 90-degree angle, one side, and one additional angle, we know the 90-degree angle and two of the sides? We'll say this side and this side. So let's call this triangle A, B, C. That makes this side little a, and this side over here, little b. That means we're trying to find little c, big A, and big B. And since we're missing both of our angles, in this example, we are going to be using inverse trigonometry. Inverse trigonometry is what allows me to go from a ratio to an unknown angle. But what are we going to use to find the missing side? Well, if you know two sides of a right triangle, you can use the Pythagorean theorem to find the missing side. So just like we used the 180-degree angle sum in the last problem, there's an alternate relationship we can use to find a missing side. We'll write 7 squared plus 13 squared equals c squared and solve the problem. Now we want to be careful here. It depends on the wording of the problem whether we should leave our answer exact, as in a radical, or whether we should round our answer to the nearest tenth. For this example, I'd rather leave my answer exact because there was nothing in the problem that I made up that says that I should round, and I'm going to avoid rounding as much as possible. So looking at the number 218, can it be simplified? And the short answer to that is no. So we would leave this answer as the square root of 218. For those of you who are going to be rounding this, or if this problem had been a rounding problem, we would say that C is approximately 14.8. Now, as I stated in the last problem, we want to use the given values to find missing information. So even though I've got an exact answer for C that I could use and a rounded answer for C that I could use, I'm going to use A and B, the given pieces of information, to find the missing angles on this problem. Well, the missing angle A has a different relationship than the missing angle B. If I'm looking from A, we would call 7 the opposite side and 13 the adjacent side. Which of the three trigonometric functions should I set up? If you thought in your head tangent, you are correct. Tangent A equals 7 over 13. Again, when we're missing an angle, we're going to be using inverse trig to find it. Typing this in our calculator and being sure that we're in degree mode gets us an answer of about 28 degrees. Doing the same thing, but instead of the perspective of A, from the perspective of B, we find that 13 is actually the opposite side and 7 is the adjacent side. So we're going to set up the same equation, except this time we're going to say tan B equals 13 over 7, and that B is equal to the inverse tangent of 13 over 7. And that gets us the answer that B is about 62 degrees. Now, with rounding to the whole, or rounding at all, we want to make sure that our angles still add up to 180 degrees, because there's a chance with rounding that they didn't. Just double check that. 28 plus 62 makes 90, 90 plus 90 makes 180, and we have successfully solved this right triangle for all of the missing information. All right, now let's get to the exceeds portion of this learning target. In this objective, we want to be able to solve right triangles in application problems. So what's a typical application problem when we're talking about right triangles? Generally, anything to do with angle of elevation or angle of depression is going to be considered an appropriate application problem. Let's talk about angle of depression versus angle of elevation. If I'm a person, I have the option of looking up or looking down. If I'm looking down, we want to sight from the horizontal and measure our angle down. This angle is referred to as the angle of depression. If instead I'm looking up, and I realize this person is looking out of the top of their head instead of where their eyes might be, we again want to refer to the horizontal, but this time we want to measure our angle up. This would be called the angle of elevation. In general, and in almost every application problem, the angle of depression and the angle of elevation end up being the same angle because they meet the relationships such as vertical angles are congruent, or alternate interior angles which are congruent, or for some reason, whatever reason, they generally end up being the same angle, same position, regardless of whether it's from depression or from elevation. So let's take a look at our first example, finding the height of an unknown object. So, a common problem. A guy wire, 30 meters long, runs from the top of an antenna to the ground. If the angle of elevation of the top of the guy wire, or of the top of the antenna, along the guy wire is 52 degrees. How tall is the antenna? Now, I've spent pretty much my entire whiteboard just writing the word problem, so I'm going to draw a teeny tiny picture over on the side. I have an antenna and a guy wire from the top to the ground. This is going to form a 90-degree angle from the antenna to the ground. I know that the guy wire is 30 meters long, so I'm going to go ahead and label that. I know that the angle of elevation, that means the angle going up from the top of the antenna along the guy wire, is 52 degrees. And the question is, how tall is the antenna? So what I'm going to do now is erase the story problem. And focus on my teeny tiny little picture. Here we go. Which of the trig ratios would best be employed to solve this right triangle? Well, I know the angle is 52 degrees. I know the opposite side, and I know the hypotenuse. The correct trig function to use would be sine. Solving gets us x equals 30 sine 52. And if we type this in a calculator, we get that the antenna is about 23.6 meters tall. That is how we use trigonometry to solve a right triangle application problem. Now, this is about as simple as the problems can get. There are more complicated problems in this, and there are problems of equal simplicity. Let's take another example. The angle of elevation, the angle of elevation to the top of a water tower from point A on the ground is 19.9 degrees. From point B, 50 feet closer to the tower, the angle of elevation is 21.8 degrees. What is the height of the tower? Now, this problem in your book comes with a picture. Point A, point B, 50 feet, 19.9 degrees, and 21.8 degrees. How can we use trigonometric ratios to solve for the missing height? Well, if you think about the water tower being perpendicular to the ground, we have not one, but two right triangles that we want to use to figure out this relationship. The book gives you a major hint because the book labels this side as x. So we have two unknown sides that we need to solve for. Let's set up the trig ratios of this smaller triangle from point B to the top of the water tower, which has been labeled point C. We have 21.8 degrees here as the angle of elevation. We have the opposite side as y and the adjacent side as x. Which trig function does this relate to? Tangent of 21.8 degrees is the opposite over the adjacent. Then we can set up a second trigonometric equation using point A. In point A's perspective, we know the opposite side is y. And this time we have to be careful with the adjacent side because from point A's perspective, the entire triangle is what's being created. And so the adjacent side is not just the 50, but actually the 50 plus x. So we can set up the ratio tangent of 19.9 is equal to y over x plus 50. It's going to take a little algebraic maneuvering to get an answer, and to do that I'm going to need some more space on my whiteboard, so I am going to erase the picture. All right, let's start with our first equation. If we multiply both sides by x, we get that y is equal to x tangent of 21.8 degrees, and that x is equal to y over tan of 21.8. Well, this is going to be necessary so that we can substitute the x out of our second equation and solve it for y. By inputting this value for x in our second equation, we get tan of 19.9 is equal to y over tan 21.8 plus 50. This is all mathematically accurate, but it is going to take a little bit of maneuvering to solve it. So what we're going to do is multiply this denominator, y over tan 21.8 plus 50, to the other side, tan 19.9. And I'm not going to use the pink because that's a little bit blurry. So we're going to switch back to the black marker. Again, we're multiplying this denominator to the other side. So now we get tan of 19.9 degrees times y over tan 21.8 plus 50 equals y. We're going to have to distribute this out and try to get our y's isolated on one side of the equation. Again, all of this is algebraic maneuvering. We've actually completed the trigonometric part of this problem. We applied our trig ratios, we understood our right triangle. From here on out, it's do we remember all the distributive property, all the relationships algebraically that allow us to solve an equation that looks like this. The trig at this point is no longer part of the question. So we're going to do tan 19.9 distributed to each value in the parentheses. This gives me y times tan 19.9 over tan 21.8 plus 50 tan 19.9 equal to y. In order to isolate the variable y, we need to collect its terms on one side. So we're going to subtract the y tan 19.9 over tan 21.8 to the other side. And then we can pull the y out of this equation. Y parenthesis 1 minus tan 19.9 over tan 21.8 equals 50 tan 19.9. All right, one more step to go, and then this whole thing can be typed into our calculator. We're going to divide both sides by this quantity right here, 1 minus tan 19.9 over tan 21.8. What that looks like is 50 tan 19.9 divided by 1 minus tan 19.9 over tan 21.8 equals y. Type this into a calculator and you get your approximate value for y. And the solution is 191 feet. Now that we've seen the trigonometry in action for solving right triangles, let's take a step back and talk about something that we haven't seen before. We've seen sine, cosine, and tangent, but until we just used it now to solve these triangles, we hadn't seen inverse sine, inverse cosine, and inverse tangent. So it's worth defining these. If x equals sine theta, then the inverse function is that theta is equal to inverse sine x. Now it's important to note, when we're talking about angles across the unit circle, this function will always output a value between negative 90 degrees and positive 90 degrees. This is a function in your calculator. That means the angles will be sent either to the first quadrant if sine is positive, or the fourth quadrant if sine is negative. Now, if you're talking about an angle that's actually located in the second or third quadrant, you would need to use reference angles and relationships to find those values. A good example of this is if we say sine theta is equal to 0.125. Now keep in mind that this kind of decimal is completely normal for a sine-cosine ratio. In fact, sine and cosine are always going to be between -1 and +1, which means 99.9% of the time you're going to be seeing a decimal between 0 and 1 for these functions. If we say that sine theta is equal to 0.125, there are actually two places on our unit circle where this value is obtained. Here in the first quadrant, and again here in the second quadrant. And that's because these two have the same reference angle. So if we type into our calculator inverse sine of 0.125, we get the reference angle that theta is equal to about 7 degrees. That could be 7 degrees here or 7 degrees here, which means that we have two answers. Theta equals 7 degrees, or in the second quadrant, theta is equal to 173 degrees. How you answer a question is going to depend on what the directions are asking. Are they asking for an acute angle, an angle between 0 and 90, or are they asking for every angle from 0 to 360? The same goes for cosine and tangent because all of these have two equivalent locations. So let's take a look at another inverse trig function. If we say x is equal to cosine theta, then we can say that theta is equal to the inverse cosine of x. Now, our calculator in this case is going to output a value between 0 degrees and 180 degrees. This is not the same as sine because cosine is not positive or negative in the same quadrants as sine. In the case of cosine, you have positive values in Q1, negative values in Q2, and so the calculator can get the whole range of cosine values by outputting an answer from 0 to 180. If I make a statement such as negative 0.5 0.55 is equal to cosine theta. I know that I'm talking about an angle where cosine is negative. That angle can be here in the second quadrant, or it could be here in the third quadrant, because in both of these quadrants, cosine is negative. If we type this into our calculator, theta is equal to the inverse cosine of negative 0.55. We get that theta is equal to about 123 degrees. Well, that's obviously our second quartile angle, but what's its equivalent over here in the third quartile? Well, this is where reference angles can really help us out. If we know that this angle here is 123 degrees, then we know the reference angle is whatever gets it to 180, which is the closest x-axis, which is 57 degrees. And we know that these two angles have the same reference angle of 57 degrees. So we can find our √3 value by asking ourselves, what's 57 degrees after 180 degrees? And we see that theta can also be 237. Both of these angles have the same cosine ratio of negative 0.55. Again, you'll know how to leave your answer based on the directions in the question. Does it ask you for all angles from 0 to 360, or does it ask you for the angles from 0 to 180? Does it ask you for the smallest positive angle, or does it ask you for more than one? There's even more ways to write our answer, but we're going to limit ourselves here for now. This should be enough information to get you through the next set of practice problems that we'll work through in class. Thank you for watching this lesson. Please feel free to email me if you have any questions.